My name's Luke.
And my name's Jake.
And today we're going to be talking about our sound matching game that we constructed. So basically what the point of this game is the computer will output a tone, and we're going to try our best to match the tone. And every time that we try and match the tone, we will get a score, and the higher the score, the farther a flag will move towards our opponent's sensor. So we're going to dive right into it and give a brief explanation on how we constructed it. So here's our entire system that we're using for this lab. We'll just start with the DAC, which is used for data acquisition. Going from left to right, we have our ground over here, which is hooked up to our breadboard. And then we have our 5-volt power supply, which is actually going to power the entire system. Then we have our 2 ports, which are hooked up to our stepper motor board over here. These are ports 1.3 and 1.2, which actually correspond to values that we have in our VI. Our green wire is going to control the direction of which way the motor is going to go every time it cycles, and the purple wire is going to control how many times it steps every time it cycles. So here we have our circuit right here with a 5-volt power coming in from our DAC. There's 2 separate sides of this, one being right here for player 1 and one being right here for player 2. 5 volts comes in from our DAC and goes through a 5.1 k ohm resistor, and this is so it doesn't burn out our photoresistor, which is right here. The main thing that we're using is this little guy, and this is a photoresistor. Essentially how this guy will work is when you hook it up to a circuit, when it's exposed to light, you'll actually get a smaller, see me just going over the top of it makes a change. You'll actually get a smaller resistance as opposed to when I cover it with my finger, we see it jump all the way to 150, still climbing. Right here we can see the purpose of our 5.1 k ohm resistor. If we were to run this without a resistor, we'd get way too high of a resistance to be able to get an output on our DAC. The most important part though is what's in between our resistor and our photoresistor, and this is our V out. And this is actually giving us the value or the reading of the photoresistor, and these are hooked up to corresponding ports AI0 and AI1, which again corresponds to what's on the computer.
Alright, so this is our photosensor VI right here. And so what it does is that it goes through the DAC and it senses if one of the photosensors is covered up. So here we have player 1 and player 2, and these are the voltages coming in actually. So if we cover up this one, player 1 goes down, or it goes up, sorry, so the resistance goes up. This one, player 2 gets covered, goes up in resistance, and as you can tell, it ends the game. So we have 2.8 as like the median for player 1, so if it is below 2.8, then it doesn't trigger the end of the game. If it's above 2.8, then it does. And same for player 2 here, which is 1. So that is like the median. So it goes from 0.58, so it's not covered, to about 1.5. So right in between there is 1. This is our random frequency generator. So we want a tone between 200 and 500, so that's why we set this up. Then we have something to simulate the signal that gets in number form. Then it'll play the waveform, then it acquires a sound from us. So it'll get a certain frequency. And over here we have a chart of the frequency. Then here's my tone, 118, and this is target tone. Then I get a 0 because that's not within 30% of what it should be.
Alright, so here we have the VI of our stepper DACs, and like I was explaining before with a brief introduction of the circuit itself, what these are actually doing is they're telling the VI. So if we go into details, we can see port 1, line 3, and that'll actually correspond with our direction on the stepper motor, which was briefly explained before in real time when we were talking about the circuit. And then it goes through both of our DACs. We have a Boolean indicator up here signaling if the sensor is dark or light, and then we have our statement down here saying if the limit hasn't been reached yet, the game will keep going, or the game will end itself.
Alright, so this is our final VI that brings all of our sub-VIs together. Alright, so this is our random frequency generator right here. So it gives us our tone. This is just an indicator. So it gives us our tone, our score, and our target tone, which you can see are over here also. This is the stepper deck that will control the steps for the game. Alright, from the stepper deck we have the game status over here. Photo sensor is covered in a start. Then it's gonna trigger this OR statement, so it'll become true and it'll stop the whole thing, or you can just manually stop it by hitting the button. And up here we have wait. It gives us a little bit of leeway between each player's turn.
Alright, so the last thing to do is to show you how the game works and actually play it. So if you want to go ahead and hit run. Ooh. Plug it in. Okay. So the thing about these motors is that if they're plugged in and just sitting stagnant, they get really hot. So what I have to do every single time that we're doing something on like the VI is I unplug it. How many times do you think it's been since I do that and it's not plugged in?
You've probably done that like 5 or 6 times already, so. Oh my God.
Round 3 of trying to play the game. Go ahead and run it. Boop. Boop. Okay, we're kind of at a stalemate, so I'm gonna just make horrible noises now. Go ahead. Boop. Bah. Yay! Jacob wins! Okay, so as you can see, our stepper motor moved over enough to be able to cover our photo resistor enough to hit the threshold. Basically what happens is, it may not be all the way covered, but the threshold was enough to be tripped and to end the game. So that's a little bit about our sound matching game. We really hope you liked the video, and we'll see you next week.